Okay, we have probably in your class, and I know in my class, we've been talking about derivatives and various derivative rules, but we're going to kind of take a step back and we're going to look at limits one more time. All right, so let's take it to the limit one more time, if you catch that reference. Okay, so we're going to talk about limits, but in order to do so, we're going to bring up something called an indeterminate form. Now, we've dealt with these indeterminate form limits before. All right, this is when we had some kind of a function, suppose f of x over x, and when we plugged in the value that we were looking for the limit, we got something like 0 over 0. You might have also received, or not received, you might have also had something like and let me fix this here, it's 0 over 0, infinity over infinity. That would have also been indeterminate. But before, we had to manipulate algebraically and try to simplify things in order to plug in the number we were looking for. Well, the beauty of this is that we can apply something called L'Hopital's rule. All right, L'Hopital was a Frenchman. It was, I believe, it wasn't L'Hopital that, L'Hopital first published the rule. All right, I believe that it was I think it was Bernoulli that actually credited L'Hopital with the rule. But anyway, at any rate, we're going to look here at L'Hopital's rule. And so let's find out what it is, and then we'll work out some problems that are actually really easy. All right, so it says suppose that f of a equals g of a equals 0 and that f and g are differentiable on an open interval. That means that you can take the derivative of f and the derivative of g. All right, and such that g prime is not equal to 0. All right, so when you take the derivative, you should not be able to get 0 in the denominator. Okay, so if that's the case, then you take the derivative again. But assuming that that is possible, that you can take the derivatives, then you can evaluate the derivative at that value and find the limit. Okay, so it's actually really neat. And I mean, maybe it sounds like a mouthful to say or to read, but let's just look at it in practice and see how it works out. So looking at this first example here, it says use L'Hopital's rule to evaluate the limit. Now, what happens when I plug in 3 right there? Well, I get 3 minus 3, which is 0. All right, I'm not even going to worry about the numerator, but I suppose that if I plug in 3 in the numerator as well, I'm probably going to get 0 over 0, an indeterminate form. But at any rate, we're going to continue this, and we're going to apply L'Hopital's rule. So let me write that, and I always write it like this L and this H to signify that I have applied L'Hopital's rule, and that is to take the derivative of the numerator and the denominator. So this is not a quotient rule by any means, okay? It's a lot easier than that. You take the derivative of the numerator and the denominator in isolation. So the derivative of the top is going to be 2x minus 8, and the derivative of the bottom is just 1 because the derivative of x is 1. Now ask yourself, can I plug in 3 into x without any problems? Well, the answer is here, yes, because you don't have to worry about 0 in the denominator anymore. So then you're going to say, well, 2 times 3 minus 8 all divided by 1, and we don't need to worry about the divide by 1. This ends up being 6 minus 8, which is -2. And so that right there is the answer for our limit here. The limit as x approaches 3 of all of this stuff here ends up being -2. And how do we know? Because we applied L'Hopital's rule. Now, you could go back to what you did before, and let me just jog your memory. All right, but this is, you'll see this is a lot easier. If I factor, meaning algebraic manipulation, suppose I have x minus 3 times x minus 5, all divided by x minus 3. So this is the algebraic manipulation route, which is a lot more work if you ask me here. Then you end up with the limit as x approaches 3 of x minus 5. And now you can plug in 3, and you get 3 minus 5, which is -2. But as you can see, it does match, okay? But the algebraic manipulation route was probably a lot harder, and it's probably a lot harder if you're dealing with something that maybe has a radical in it. So kind of keep that in mind. All right, so let's take a look at a couple more examples and see where we're at. All right, the next example, oh, I really like this one. This one is a trig example, and so let's go ahead and pull up our unit circle. Let me get that in here. All right, so what we're going to do is we're going to apply L'Hopital's rule. All right, applying L'Hopital's rule there, and let's take the derivative because I know I cannot plug in 0 in this denominator because I'm going to have 0 squared. And so you're actually going to have to take the derivative a couple of times, all right, just so you're ready to go about doing this. So let's see, limit there. The derivative of the cosine of 7x. So I know the derivative of cosine is sine of 7x, and then I need to multiply by the derivative of the inside, so derivative of 7x is 7. All right, and it's actually going to be negative because the derivative of cosine is negative sine. So there's my negative. All right, and I follow the chain rule. The derivative of -1 is 0. The derivative of the denominator, x squared, is just 2x. But again, I can't plug in 0. So again, I'm going to have to apply L'Hopital's rule. And you'll go ahead and do that until you can actually take the derivative. Now, you may find that the limit actually does not exist. So that may be one thing that you'll run into. But generally speaking, when you've got this kind of L'Hopital problem, you'll be able to take the derivative. So let's see here. Let me move this unit circle out of the way for a second. Move it this way. Okay. And let's see. Let's apply this here. If I have the derivative of sine, the derivative there of sine is cosine. So I'm going to have cosine of 7x. Okay. And I have a -7 in the front. And I'm going to multiply that by the derivative of the inside, which is 7. And then divide that by the derivative of 2x, which is 2. So this ends up being, let's see, -49, right? The limit as x approaches 0 of -49 cosine of 7x, all divided by 2. Now I'm ready to evaluate. I can plug in the 0 right in there. I get something like -49 cosine of 0, all divided by 2. Okay, so now I need to look at my unit circle. And let's see here what that looks like here. And so as we zoom in here, the cosine of 0 is this value right here, 1. So the cosine of 0 is 1. And we're going to go back over here. If this right here, cosine of 0 is 1, then we are left with our answer, which is -49 over 2. And so that right there is the answer for this limit of indeterminate form, applying L'Hopital's rule. All right, and now let's take a look at another example. So let me pull this example up to the top, and let's see what this one looks like. Another trig limit, but that's okay. They're actually kind of fun when you already know all of the derivative rules, right? So again here, when we plug in sine of 4 times 0, that's going to be 0 by the unit circle. So we yet again have to apply L'Hopital's rule. And so we go ahead and do that. We have the limit as theta now approaches 0 of derivative of 2 is 0. -2 is the coefficient of the cosine of theta. So let's look at the cosine. Derivative of cosine is negative the sine. So it's going to be a negative sign. So we have -2 times negative sine of theta divided by, and the derivative of sine is cosine. So cosine of 4 theta times 4. All right. So by the chain rule. So we end up with something like this. The limit as theta approaches 0, it becomes +2 sine theta. All right. Divided by 4 cosine of 4 theta. And now we can plug in our theta approaches 0. So we're going to say then that 2 sine of 0 divided by 4 cosine of basically 4 times 0, which is just 0. All right, so I'll just put 0 there. All right, and you look that up again on your unit circle, and the sign of 0, as we go back over here, sign of 0 is, let's see here, sine of 0 is 0, cosine of 0 is 1. So we're going to need that, okay? So sine of 0 is 0, and cosine of 0 is 1. So we don't no longer have a 0 in the denominator. We actually end up with a 4 in the denominator. We have a 0 in the numerator because 2 times 0 is 0. So we end up with our answer, which is 0 for this limit of indeterminate form. So really nice examples here, applications of what we call L'Hopital's rule. When we're working with indeterminate form limits, again, no need for any kind of algebraic manipulation because we apply L'Hopital's rule by taking the derivative. So, as always, I hope this video was helpful. And remember, like and subscribe.